Hello, everybody. How you doing? This is my first attempt at recording a lesson, so I hope it's going to be very clumsy. But Math 60 students, this is about section 3.7. I'm going to tend to be kind of rapid because I know that you have a pause and a rewind and all that stuff. So this is going to be a section on applications. We are looking at, first of all, I've broken it up as an introduction. Let's read it together. It is important for us to understand that the derivative of a function is more than just a mathematical concept. It has applications anywhere in science or business. The rate of change of one unknown as compared to another is unknown is studied. Okay, so that was clumsy, but here we go. The types of problems we'll see are motion, particularly, and then there's geometric shapes, and then they give you other formulas as well. So these notes, you can look at them and you can keep them. I actually uploaded these also to Canvas. But anyway, these are notes that we should know about motion problems. I see my notes are messed up, but oh well. Gonna have to fix that later. Anyway, so we have, if we want to find, if they're given a position function, we want to derive it to find the velocity function there. If you derive the velocity function, that's the second derivative of the position function, you can get the acceleration function from that. A couple more notes that help you with the homework. A particle at rest means the velocity is equal to 0. If they ever ask you that, then you just set your velocity function equal to 0 and solve it. So you're going to go v of t, I'm going to set it equal to 0 and solve. A particle is speeding up at any moment. The velocity and the acceleration share the same sign. Otherwise, it's slowing down if they have opposite signs. Now we're going to try to make sense out of that, because the velocity is telling you how much the position is changing with respect to time. So if it's like 32 feet per second, every second you're going 32 feet in the positive direction. You could also be going in a negative direction. So for example, a ball that's hit up and then comes back down again, you have a positive velocity, and you could have then a negative velocity because of your change of position on a number line. The acceleration is telling you how fast the velocity is changing. So if the velocity is positive going up, but the acceleration is saying, hey buddy, you got to go down, the acceleration will actually be pointing in a different direction than, say, the velocity. So an easy solution is to just check the signs of your acceleration and velocity to see if you're speeding up or slowing down, and they ask those kinds of questions as well. There are also geometry problems, and we'll get to those, but it's interesting to note, more edit there, that we are what's going to happen in those geometric problems is that the dimensions of a shape are going to change with respect to time, which is crazy. Like, for example, a soap bubble is expanding with time, or a rectangle is shrinking, or whatever it's doing. So it's a game that we play, and it leads us ultimately to another section called related rates. And then finally, there are other relationships, such as the gas law and gravitational rule and all that stuff. But I want to get to the works. I want to help you guys out. So let's do the first one I chose to do is something I made up, I guess. And this guy is basically a typical problem from this section. It says, given the position function s of t is 1/3 t cubed minus 1/2 t squared minus 2t plus 1, find each of the following. And we'll take this on one at a time. So I think you know what to do for velocity, right? So the velocity is the derivative of the position function. Tells you the rate of change of your position. So if we derive s of t up here, then we're going to get no, we're not. We're going to derive it, Weber. So it's going to be t squared minus t, and then minus 2. There you go. This is our velocity function. You know, it's good to see them side by side, so I will bring this guy down as well. S of t is your position. This guy just tells you where you are on a number line, let's say in one dimension. Okay, I'm just copying this down. Okay, so there's that guy, and they're all related. It's a family of functions. Hey, part B says, what's the acceleration? Well, The acceleration function is really the derivative of velocity, which of course is the second derivative of position. So in that case, we get what? 2t, I'm deriving the velocity, minus 1. So that is our acceleration. So part B is done. So it's easy, kind of, if they're polynomials in particular. It's easy to find those guys. Now it gets a little more interesting. The position, velocity, and acceleration function of the particles. So they're asking us to find the position, the acceleration, and the velocity, and the velocity of the particle at time t is equal to 3. Now I don't have my calculator, so I may not be able to do some of this, but let's go with position first. So the position at time t is equal to 3 would be found by plugging, guess what, 3 into your position function. So we're talking about 1/3, and then 3 cubed is 27, say, minus 1/2, and 3 squared is 9, and then minus 2 times 3, and then plus 1. You guys figure that out for me, would you? 9 minus, you know me, 9 minus 9/2, right? 9/2 minus 6 plus 1. I know that 9 minus 9/2 is another positive 9/2. Did you know that? This is minus 5. So what we have is that's 4. I think we're at negative 1/2. If I'm wrong, send me an email. That's position. The velocity. So the velocity, let's do that. Use the words. So the velocity at that point, right? That's where you are. The velocity is v of 3, and that's equal to, I'm going up to here now with the velocity. It is 3 squared is 9, minus 3 minus 2. That looks like it's 4. Now, if I give this any kind of, it looks like there are no dimensions here, so I could say something like this is meters, maybe, and in that case, maybe this is meters per second. I maybe would improve the problem by doing that, okay? If I were to give it on a test or something. Okay, so give the dimensions. So yeah, we're talking about 4 meters per second at that precise moment. Okay, and then finally acceleration. Okay, so acceleration is a of 3, and that means what we've got is 2 times 3 minus 1, and it's looking like 6 minus 1 is 5. Watch how this goes. Meters per second, or meters per second squared, they call it. So that's part C done. All right. Okay, when is the particle at rest is part D. So when is the particle at rest? That is, remember what we said up here, way up here in the notes, at rest means the velocity is 0. So we set the velocity function equal to 0 to figure that out. So at rest, when velocity equals 0, so we take velocity, which is equal to t squared minus 2t minus 2, set it equal to 0. I'm going to have to start saving room, I think, for these. Oh, we've got room. Okay. So that's a 0. Okay. Well, that looks like a quadratic, so it's going to factor nicely, I bet. We've got t, oh, did I do a bad problem? Oh, no, it doesn't have a 2 in front of there. Oh, thank goodness. Okay. T squared minus t minus 2, so we have t minus 2t plus 1. So it is at rest when, spell when, t is equal to minus 1 or 2, guess what? Seconds. Now we're probably going to start the stopwatch or whatever, that's a weird thing to say, tick, 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 0, 1, 2, so I'm probably going to be interested in the interval, but that's okay, we'll just leave it generic right now, go back in time 1 second and it's at rest again. We're doing pretty good. So E, when is the part, okay, this is where they ask about the speeding up and slowing down stuff. Okay, so E, for this one, remember, when you're dealing with speeding up and slowing down, the notes on the first page are going to say, hey, look, I need to check the sign of the two functions, velocity and acceleration. Oftentimes what people do is they just set up, like, here's velocity, and they set up a number line, and we've got like -1 and 2. That's where velocity is 0. Okay, and then you just check the sign. We're checking the sign by plugging into velocity, and velocity is t minus 2 and t plus 1. If I plug in a minus 2, like t is equal to minus 2, I'm interested in knowing if the velocity is positive or negative. Well, it's easy to check. I just do this. I go, let's see, if I plug in a minus 2, I've got a negative, and then a minus 2 times another negative, so the whole thing is negative. So the velocity is negative there. If I do the same thing, you know how this goes. This is actually an algebra thing. If you go like t is equal to, you can even choose 0, time t is equal to 0. What's the velocity at that moment? Well, negative times a positive. Do you see what I'm seeing? A negative, if that's 0, negative 2 times positive 1, it's negative. So, oops, what am I doing? I'm tripping. This is my very first one. Forgive me. Velocity is actually positive there, then it's negative, and then finally you try, say, t is equal to 3 maybe, and you get a couple of positives, don't you? You get a positive 3 minus 2 and a positive 3 plus 1. So the whole thing is positive again. Now you're not done because you're worrying about whether it's, whatever, slowing up or speed, or whatever we said. Okay, sorry, I'm kind of caffeinated. All right, now we take a look at the acceleration function. He's pretty easy. This guy's just, where are you, accelerate? There, where is he? Gosh, that went all the way up. Okay, let's see. Acceleration, where are you? And he's a little bit, 2t minus 1, I thought so. So it's 2t minus 1. The only place where acceleration is 0 is when t is 1/2. That's the divider. So 1/2 is about here. I'm comparing it to the two, I'm comparing the two of these guys. I only have two colors, it looks like. This way and that way. And I'm plugging in numbers. So let's say I plug in the number t is equal to 0. 0 gives me a negative acceleration, and then in the next case we've got, let's try t is equal to 1, and of course if t is equal to 1 we get a positive acceleration. Now here's the thing, for speeding up and slowing down, you want to compare the intervals in both of these guys. Where's it positive, where's it negative? So let's say we focus on t is in the time interval 0 to, say, infinity. I don't care about negative time. So let's just start at 0. So that means if we can, I wish I had another color, but I'll try this marker. I'll go, okay, 0, we're talking from 0 and going that way. That's supposed to be an arrow. So we're supposed to be going in that direction. Won't let me write on the highlighter. Okay. So as I can see that the velocity is negative from 0 to 2. The acceleration is negative from 0 to 1/2. So really on, oops, wrong thing. Let's get rid of him. Erase that. So on 0 to 1/2, say, velocity and acceleration are greater than 0. They're both positive. So it's actually speeding up there. But then something happens to acceleration. It turns, they were both negative, right? Both negative. But then what happens is acceleration changes positive while velocity is negative still. Velocity is negative till it gets to 2 seconds. Acceleration switches to positive when you get to 1/2 second. So on that interval, from 1/2 to 2, they have opposite signs. So on 1/2 to 2, velocity is actually, and I have this sign wrong, I thought they were positive. So they're both negative on the first interval. Now the velocity is still negative, but the acceleration has turned positive. So now they are slowing down. The object is slowing down. Okay. Then, if you look at here, finally what happens is the acceleration being positive turns the particle to move in the positive direction. from 2 onward, we've got the velocity's positive and so is the acceleration. So that's what we say. On the interval from 2 to as far as you want to go, velocity and acceleration are both greater than 0, and so now it's speeding up again. So we have this feeling of, it's moving in a direction, in a negative direction, and then it slows down to 0, and at time t equals 2, and then moves in a positive direction after that. So the very last problem is saying, hey, I want you to graph this thing as some sort of motion along a number line. Okay. Well, all right, we're running out of time, unfortunately. I guess I can write it here. But if you have a number line, if you plugged in 0 into the position function, which is way up here, you would get 1. So I'm thinking I can sketch this out by doing a table. I can go, here's t, here's s, here's v, here's acceleration. You don't need all that. But you can go like 0. Oh, it's not going to let me write onto this page. Okay, that's the way that goes. You can start at 0, and I think what I'll do is s is equal to 1. And so you have a number line that says this is 0. And okay, my starting position t is equal to 0. I'm at 1 on the number line. But you're going in a negative direction. In fact, from 0 to 1/2, you're in accordance with each other. When does it turn around? The velocity at 2, when t is equal to 2, what do you get? Here's a tough calculation. S of 2. Plug in 2, you get 8/3, you got all that stuff. I think I'll let you figure out the points. I might pause and do it. But basically, you're going to have a curve that's going to go negative a certain distance and then come back again. It'd be nice to know what that point is. Maybe put another point in there. T is equal to 2 is important, and then after that, who cares? But we have this diagram of it moving in the negative and then slowing down and moving in the... So it's slowing down to 0 and then moving in that direction. Okay, so that's a lot of talking for that problem, but there are multiple parts. I can tell this is going to be a long video, but you can fast forward. Okay. Now this is a thing that I dreamt up. You have any questions? Sorry, you're going to have to rewind and see what I'm talking about. I'll try to do better as we go. It's your turn. So for this one, I'm going to let you guys pause the recording, maybe look over what I did, and then try this one as a learning experience. This would be what we would do in the classroom is, now you guys try it. So pause. I said pause. Okay. And then I'm going to do this one. So if I'm going to do the same thing, I'm going to say, I'll do less talking now. Here's a emphasis what we just did. So the velocity in this case is looking like t squared, right? And then we have minus 5t minus 6. That's part A. Part B, the acceleration is equal to 2t minus 5. Okay. Other questions were, when is it at rest? No, they want to know at 3. You don't have to do that. What I want to do is let's focus on where we're at. That would be cool to do. So let's study the sign. Get that out of there. I don't know what that is. Let's study the sign of this guy. I'm going to skip that. I think it's problem D. Doesn't matter. Yeah, D says, oh, when is it at rest? That's a good one. But really what I'm going to do is I'm going to go off-road and I'm going to study the sign of velocity. Okay, so I would set it equal to 0. So when is it at rest, really? So this is part D. That is supposed to be a 6. Set it equal to 0. Factor. See if you got the same answer. It looks like we've got a t, minus 6t plus 1. So that happens at t is equal to negative 1. Who cares, really? And 6. 6 is interesting because 6 seconds into this flight, well, this is a strange thing. Look at that. I've never seen that happen before. I don't know what happened. Let me erase that. Obviously, I don't know what I'm doing with this. Let's try it again. So we're doing this. Okay. And I write here, and it's staying there. That's a problem. Okay, that's a problem in my recording. I don't want it to do that. I'll have to edit. Oh, there we go. Okay, cool. So let me do that again. Okay, v of t is equal to, what did we say, t squared minus 5t minus 6, which is set equal to 0. And so we have t minus 6 and t plus 1. So again, we got t is equal to -1 or 6. Okay, oh, thank you. So I don't care about the -1, but on a number line, let's say we started at 0 and then we go to 6 seconds, right? This is the t-axis. I'm looking at the sign of the velocity. So for instance, if we plug in something less than 6, like say 5, then I look at it, I go 5, that's a bad 6, but that's a 6. 5 minus 6 is negative. So this once again is a negative velocity. And I bet 7, if you go t is equal to 7, you get a positive velocity. Okay, cool. Now we drop down on the same number line, 0 to whatever, and we study the sign of the acceleration. So this was velocity, and this is going to be acceleration. And it's kind of easy to see, but okay, if I take this guy down, okay, I set 2t minus 5 equal to 0. We get t is equal to 5 over 2, which is really 2.5 seconds. So at 2.5 seconds, which is about here, let's pretend, 2.5, we have a change in the sign of the acceleration. So if I plug in a 3, 6 minus 5, if I plug in a 2, it's going to be negative. So that's going to be negative acceleration. And then I bet this is positive by plugging in, say, this I thought t is equal to, say, 2. If t here is equal to 3, well, that's positive acceleration. So you can see by looking at the two graphs, one on top of the other, you can tell where things are speeding up and slowing down. I forget which question letter that was, so let me go look. Boy, this thing is funky. Okay. Yeah, we're going to talk about, that's problem E, and then F is a graph, I guess. So, can you figure this out? We've got both negative until 2.5 seconds, so on 0 to 2.5, we're speeding up. I don't care that it's negative. It's speeding up in the negative direction. Maybe put that too, negative direction, just for color. But then, between 2.5 and 6, they're opposite in sign. Velocity is saying I'm still going negative, but the acceleration is now pointing in the positive, slowing them down. So the rate of change of the velocity is changing in the positive. So now we're going 2.5 to 6, slowing down. We're still going negative direction, but slowing down. And then finally, after 6, we're all in agreement there. 6 to, as far as you want to go, it's speeding up again. Now, you don't have to do this part, but it's fun to figure that stuff out. And then you can plug the points in and see what's going on. You'll have a graph that is similar. I'm really kind of not wanting to plug in the numbers. I should have done that before the video. But basically, finding the position precisely where it is kind of cool. And you can play around with that and look at, ask questions if you want to see that done. So F, well, why not? I can do this kind of quick, even though the video is kind of getting lengthy, of course. I'm worrying about a lot of different things. Okay, so we've got S is that crazy thing. So if we build a table maybe up here and decide to go, the guys that I'm interested in are, 0 and 6 maybe. So S, well, no, let's do T and S. Let's do it over here. T and S, I want to know. So 0 and 6. When you plug in 0, he's easy enough. He starts at 4. It's the 6 I want to give you guys to do. So that's 6 cubed. Ooh, we got a little big. Okay. Wow, that's wild. There it goes again. 6 cubed. There's something I don't know about. Okay. over 3 minus 5 over 2 times what? 36, and then minus 36, and then plus 4. Whatever that number is, put it here. I don't know what it is. Got, let's see, that's 36 and 90, 108, minus 5 times 36, and then minus that. Okay, it's negative. That's all I can tell you. So this guy on a number line, you would say, I'm starting first of all at 4. Here's 0. I'm starting at 4, and then my path would be, this one is when t is equal to 0, but it's going to head in this direction to some mystery point that I was too lazy to figure out, where t is equal to 6. It's at rest now, the velocity. It's not moving, and then it just cruises in that direction after that. So that's the motion that's going on. Okay. All right, this is going to be an MP4 file. I don't know how big it's going to be. I said to do problem number 8 on page 233. So we can do that. You can get your books going. If a rock is thrown vertically upward from a surface of Mars with a velocity of 15 meters per second, its height after t seconds. So this is the height. This is the height is equal to, let's see, where are you? S is equal to, I'm trying to get the right problem, so beg your pardon, number 8. Okay. What